In this video, we will discuss the reactions between acids and bases. In a reaction between a strong acid and a strong base, the products are essentially water and some sort of ionic compound that is dissolved in aqueous solution. As an example of this, we can take a look at the reaction between hydrochloric acid and sodium hydroxide. The balanced reaction that you see here is written as a single-headed arrow because essentially the reaction goes to completion and produces a salty aqueous solution. The stoichiometry between the acid and base is 1:1, and likewise it produces one equivalent of water as a result. The reaction that you see here is referred to as the molecular reaction or the molecular equation because the formulas of the compounds are all written out in their non-ionic form, but indeed the strong acid and the strong base are strong electrolytes, so there's another way that we could write this reaction, and that is in terms of a complete ionic reaction where we dissociate the strong electrolyte species and show them as their component ions. So, for example, the hydrochloric acid is in the form of H plus and Cl minus. The sodium hydroxide is in the form of sodium ions and hydroxide ions. On the product side, the sodium chloride is shown as its ions, but since water is a molecular species, that's written as a complete just molecular formula. You see that on the reactants and product side, there are sodium ions and chloride ions that appear to be unchanged. These are the so-called spectator species, and these are the ions that can be removed to write another reaction, which is referred to as the net ionic reaction, which involves the reaction of hydrogen ions with hydroxide to form water. As another example of a reaction between a strong acid and strong base, we can look at the reaction involving hydroiodic acid and calcium hydroxide. These reactions are sometimes referred to as neutralization reactions because the resulting solution is neither acidic nor basic, but simply a salty aqueous solution. The Hi is the acid, the calcium hydroxide is the base in this case, but the stoichiometry for this particular reaction is 2:1 because the calcium hydroxide has two hydroxides in the formula, therefore requiring two of the Hi to do the neutralization. The salt is calcium iodide, and of course the final product is the water. Most ionic compounds are good electrolytes and dissociate into their component ions. So, in fact, then we can write the complete ionic reaction for this reaction by breaking apart the hydrogen and iodide in the acid and the calcium hydroxide in the base, taking into account the stoichiometric coefficients. And then on the product side, the calcium and the iodide are dissociated. The only species not dissociated in this reaction is the aqueous or the liquid water. So if we cancel out the spectator ions, which are the calcium and the iodide, we can then end up with our net ionic reaction, which if we then reduce this down to the lowest whole number ratio by dividing all the coefficients by 2, we can then end up with our same net ionic reaction as we had previously. We can then compare the reaction of a strong acid and a strong base to that of a weak acid and a strong base. And as you see here, we have the reaction between hydrofluoric acid and lithium hydroxide, producing, again, an ionic compound, lithium fluoride, and water. The crucial difference here is this reaction is an equilibrium because the weak acid HF is not completely dissociated in aqueous solution. So the molecular reaction is written as you see here, but if we then recognize that the HF is the weak acid, lithium hydroxide is the strong base, we are producing a salt and water just like we did before. But now when we write the complete ionic reaction, we're only dissociating the strong electrolytes. The weak acid is going to remain primarily as the molecular species HF in solution. So, and likewise the water, which is on the product side. So we end up with, again, an equilibrium, but there are the ions of lithium and hydroxide on the reactant side, and then on the product side we have lithium ions and fluoride ions. The spectator ions in this case are the lithium ions, and they can be removed from this reaction, and then we can write the net ionic equation as HF, the weak acid, plus the hydroxide from the strong base, and this produces fluoride and water. For most reactions between an acid and base, the products are generally a salt and water, but there is one important exception to this, and that is any reaction involving the ammonium ion and related compounds. So as you see here, between the reaction of the strong acid hydrochloric acid and the ammonia, the transfer of hydrogen ions from the HCl to the base NH3 produces an aqueous solution of ammonium chloride. So we have our strong acid, but the ammonia is a weak base, and the product, of course, is a salt in this case. If we write the complete ionic reaction by dissociating the strong acid and the salt, we then can notice that we have a spectator ion, the chloride ion, so we can cancel that out of the reaction to then end up with our net ionic reaction, which involves a proton reacting with ammonia to form the ammonium ion. In certain cases, the acids can be polyprotic acid. In other words, there's more than one ionizable hydrogen ion. And so in this case, the stoichiometry of the reaction has to be adjusted to account for that. So, as an example, if we take phosphoric acid, which is a triprotic acid, and react it with sodium hydroxide, it turns out that the first hydrogen ion comes off relatively easily to produce sodium dihydrogen phosphate and water. And so in this particular case, we have a weak acid reacting with the strong base sodium hydroxide, producing this so-called acidic salt, all right, which itself is a weak acid, and of course forming water. In addition, it's possible to add 2 equivalents of sodium hydroxide to phosphoric acid to produce another ionic compound as a product, in this case disodium hydrogen phosphate, which is also a weak acid in itself. And likewise, we could do a third reaction where we add 3 equivalents of sodium hydroxide to phosphoric acid, and that produces the ionic compound sodium phosphate.